Welcome to Lesson 3 of AP Chemistry, where we dive into the fascinating world of chemical bonds. Exciting, isn't it? Imagine this. Every single thing around you, from the air you breathe, the water you drink, to the chair you're sitting on, is made up of atoms. And these atoms aren't just floating around independently, oh no, they're social butterflies, constantly interacting and forming relationships with each other. These relationships are what we call chemical bonds. Chemical bonds are the glue that holds atoms together to form molecules and compounds. They're the reason we have water to drink, oxygen to breathe, and even the screen you're watching this video on. In this video, we'll be delving into the three main types of bonds that atoms can form: ionic, metallic, and covalent bonds. Each one unique, each one fascinating, and each one incredibly important in the world of chemistry. So buckle up, chemistry enthusiasts, as we embark on this intriguing journey of understanding chemical bonds. Scene script. First up, we have ionic bonds, the bonds that are not afraid to give and take. Imagine a world where sharing is a foreign concept. That's the world of ionic bonds. Instead of sharing, they believe in a full transfer of ownership. It's a bit like a magnanimous friend who gives you their favorite book, saying they want it to belong to someone who will appreciate it just as much. Ionic bonds form between atoms of elements that are on opposite ends of the periodic table. On one side we have the metals, always ready to lose an electron or two. On the other side we have the non-metals, ever eager to gain those extra electrons. When a metal and a non-metal meet, they don't shake hands, they exchange electrons. The metal atom loses an electron and becomes a positively charged ion, while the non-metal atom gains that electron, becoming a negatively charged ion. And voila! We have an ionic bond, a bond formed due to the attraction between these oppositely charged ions. Now let's talk about some characteristics of ionic bonds. They form crystalline solids at room temperature, have high melting and boiling points, and conduct electricity when dissolved in water or melted. And you know how some people are strong because they've been through a lot. Ionic compounds are strong because of the strong electrostatic forces holding the ions together. Predicting ionic bonds is like predicting the ending of a classic fairy tale. If you have a metal and a non-metal, chances are they're going to form an ionic bond. Look for elements that are far apart on the periodic table. The further apart, the more likely they are to form an ionic bond. So, remember, ionic bonds are all about the transfer of electrons. Quite generous, don't you think? Next in line, we have metallic bonds, the party bonds. Imagine a dance floor where all the dancers are free to move around and mingle. That's exactly what happens in metallic bonds. These are not your typical bonds, they're more like a social gathering of atoms. Metallic bonds are the forces of attraction between free-moving electrons and positively charged metal ions. Think of it as a sea of electrons flowing around a grid of positive ions. This is known as the electron sea model. These free electrons give metals their unique characteristics. For example, have you ever wondered why metals are excellent conductors of electricity and heat? That's because these free electrons can move and carry electrical charge or thermal energy from one place to another. And let's not forget about the malleability of metals. Ever noticed how metals can be hammered into thin sheets or drawn into wires? That's also thanks to the electron sea model. When a force is applied, the ions can slide past each other without breaking the bond, because the electrons can readjust around them. Now, not all metallic bonds are the same. The strength varies depending on the number of free electrons and the size and charge of the metal ions. So, metallic bonds are the life of the party, with electrons free to move around. Groovy, right? And finally, we have covalent bonds, the bonds that believe in sharing. Now imagine you're at a party and there's only one slice of pizza left. You could fight over it, or you could do the noble thing and share it. That's what atoms do when they form covalent bonds. They share electrons. How polite. Covalent bonds occur between two non-metal atoms which have similar electronegativities. These atoms share one or more pairs of electrons to achieve a full outer shell, or what we call a stable electron configuration. It's like they're saying, hey, we both need something. Let's share and make both our lives easier. The number of shared electron pairs determines the type of covalent bond. A single bond, where one pair of electrons is shared, a double bond with two shared pairs, or a triple bond with three. And just to clear any confusion, when we say single, double, or triple, we're not talking about your relationship status. Now let's talk about the characteristics of these sharing bonds. Covalent bonds are generally stronger than ionic bonds, giving covalently bonded substances high melting and boiling points. They also don't conduct electricity when dissolved in water, so don't even think about trying to power your phone with a covalently bonded substance. Another interesting thing about covalent bonds is their directionality. Unlike ionic and metallic bonds, which don't care where they are headed, covalent bonds are very directional. They are like that friend who always knows where they want to eat. This directionality gives molecules a definite, predictable shape, which is crucial in many biological processes. So, to sum it up, covalent bonds are all about atoms sharing electrons to achieve stability. They form between two nonmetals, can be single, double, or triple depending on the number of shared electrons, and they give molecules a definite shape. Covalent bonds always sharing and caring, sweet, isn't it? Now that we know our bonds, let's get to know them a bit more intimately. When you think about a bond, whether it's ionic, metallic, or covalent, it's not just a static connection. It's a dynamic relationship, and like any good relationship, it has its ups and downs. The ups and downs in this case refer to bond length and bond energy. Bond length is the distance between two atoms when the energy is at its lowest and the bond is at its strongest. In a perfect world, atoms would always prefer to be at this sweet spot. But alas, we don't live in a perfect world, and atoms are constantly jostling and vibrating, leading to variations in bond length. Which brings us to bond energy. Bond energy is like the amount of effort it takes to break up a well-established band. It's the energy required to break a chemical bond and form neutral, isolated atoms. Different bonds require different amounts of energy to break. For instance, breaking a bond in a rock band might just take a creative disagreement, while breaking a bond in a family might require a lot more energy. But there's one more player in this game we haven't talked about yet: lattice energy. Lattice energy is like the glue that holds ionic compounds together. It's the energy required to separate a mole of a solid ionic compound into its gaseous ions. The higher the lattice energy, the stronger the ionic bond. Think of it as the energy it would take to separate a team that's been winning championships together for years. Now, why are these concepts important? They allow us to understand and predict the properties of substances. For instance, substances with large lattice energies tend to have high melting points. Bond length and bond energy can help us predict the reactivity of a substance. So the next time you look at a molecule, don't just see a bunch of atoms stuck together, see a dynamic, vibrating, energetic relationship. And that's how you get up close and personal with chemical bonds. Intriguing, isn't it? Finally, let's put on our artist hats and learn how to represent ionic solids and alloys. Now imagine you're a miniaturist, and your canvas is the world of atoms and ions. Ionic solids, those composed of positive and negative ions, can be represented as a repeating pattern of these ions called a crystal lattice. Picture a three-dimensional chessboard where each square is an ion, and the pattern repeats in all directions. Alloys, on the other hand, are a blend of metallic elements like bronze, which is a mix of copper and tin. In our particulate model, we can represent this as a sea of electrons, where the copper and tin atoms are floating. It's like a fruit salad, where the copper and tin are the fruits, and the electrons are the juice making everything flow together. And voila, you've just learned how to draw in the language of chemistry. Impressive, right? Well, that's a wrap on Lesson 3 of AP Chemistry, folks. We've delved into the fascinating world of chemical bonds, be they ionic, metallic, or covalent. We've explored how to predict bond types and examined the intricacies of bond length, bond energy, and lattice energy. And let's not forget the visual feast of representing ionic solids and alloys using a particulate model. So we've covered a lot of ground, but remember, chemistry is all about making connections, quite literally, so keep bonding and see you in the next lesson.